damn it. All right, so we've looked at the first associated electrical component, that is resistors, and we talked about it extensively. Now we are going to look at capacitor. A capacitor is also an equally important electrical component when it comes to electronics. Now, what then is a capacitor? So we are looking at an electronic, so an electronic component or device which consists of a parallel plate with a dielectric dielectric material between the plates. So when we are talking about capacitor, so let's say we have a plate here, we have another plate here. Then there is a material in between the plates. So we call this material dielectric material. So we call it dielectric material. So dielectric material. Now, what the capacitor does is that it stores charges. So it stores electric charges. So electric charges are stored on the plates. Now, it will only store electric charges when an electric field is created. When an electric field is created. So in basic terms, you can even construct your own capacitor in the house. Where you get, let's say, a two plate of almost the same dimension and cross-sectional area. Just get a dielectric material in between them. Then connect it to a source of current. So the source of current is going to provide us with what we call the electric field. Now with that, there's going to be build-up of charges on the plate. So there's going to be build-up of charges on the plate. Now the dielectric material is supposed to prevent the charges from crossing over. So this material here helps in the accumulation of the electric charges. Now these charges are stored temporarily. So they are stored temporarily. The charges are stored temporarily. And it will be dissipated. So you connect the capacitor to an electric field, charges will be built up. So in that case, the electric charges will be stored. Now, after some time, the charges will then be what? Dissipated. So we have the charging state, and we have the discharging state. So that's basically the work of a capacitor. Do you get it? That's basically the work of capacitor. Now, the measure of charges stored. So the measure of charges stored per an electric field. Yeah, an electric field is called capacitance. It's called capacitance. And the unit is what? Farad or capital F. So when we have a capacitor, let me use the symbol. So this can be the symbol of a capacitor, this, or you can use this symbol. So just as you can see here, is a capacitor. Just as you can see, that's a capacitor. And in real life, this this is also an example of a capacitor. So you see, it has each rating that is 330 microfarad. Now we need to know some things about the capacitor. We need to know some things about the capacitor. So we need to know some things about the capacitor. So one is that capacitors are rated. So just as you can see on this capacitor is 330 microfarad, 240 volts. So sorry, 25 volts, not 240, 25 volts. So what the readings here means that if you connect this capacitor to a 25 volts, then you are going to get this amount of capacitance stored. Those are the maximum. When you exceed this, then it's going to cause harm to the capacitor. So capacitors are rated. Now, how do we rate the capacitors? One is based on the amount of charges that can be stored. That can be stored. Then two, it also depends on the voltage handling capabilities. So just as I said, if you look at this capacitor, it has a 25 volt maximum limit. If you connect this capacitor to let's say a 30 volt, then you are going to cause harm to it because it cannot handle voltage above what 25. Then the third um, property that we use in rating the capacitor is the dielectric material. Dielectric material between the parallel plates. So if I have, there are some capacitors, their dielectric material is simply air. You get it? So if I have a capacitor that I have, foam, let's say foam between them, the charges that will be built up will be different from the one that has um, air as its dielectric material. Now we are saying that this is what you need to note. When I connect a capacitor to a direct current source, when I connect a capacitor to a direct current source, so I connect it to a direct current source, there's going to be charges that is going to be stored. So charges will be stored when it is a DC electric source or DC current source. But when I connect the capacitor to an AC, when we talk about AC and DC, so DC stands for direct current, DC stands for direct current, and AC will stand for alternating current, alternating current. So when I connect my capacitor to an AC, because it's alternating, there's not going to be any charges stored. No charges will be built up. No charges will be built up when I connect my capacitor to an AC source. Why? Because for AC, at a point, positive charges will be built up here. At a point, at that same time, negative charges will be built up here. Now, when there is a change in the direction, when there is a change in direction in the AC, so assuming when this changes to negative rather, sorry, not positive, when this changes to negative rather, when it changes to negative, and this becomes positive, then negative charges will be built up here, and it will go and neutralize the positive charge that was already built up here. And when here changes to positive, positive charges will be built up here, and to go and neutralize the negative charge that was already built up there. So when I connect a capacitor to an AC source, I should put it at the back of my mind that there is not going to be any charges stored. So charges won't be stored. So let's look at this. You see, in the olden days, this fluorescent bulb that we used to have, immediately the light goes off, the bulb also goes off. When there is light out, the bulb will eventually go off. But now you realize that the new bulbs, the LED bulbs that we have, when the light goes off, the bulbs are still working. Why? Because in this case, there are there are device within the LD bulb, or there are component within the LD bulbs that is changing the AC current within it towards to DC. Do you get it? It's changing the AC current within into DC. And so the capacitors stored in these LED bulbs are able to store what charges. And so when there is light out, these stored charges will be dissipated and there will still be light, or your bulb will still what? Lit. Now, we have several ways for calculating capacitance. The first is the electrostatic equation. That is Q is equal to CV. That is the charges that is stored. The Q is for charges. The charges that will be stored is equal to the capacitance of the capacitor and the what? The voltage. So just as I said, the voltage is very important and the charges that is stored. So these two will influence the capacitance of the device. So yes, just as I was saying, we have this equation Q is equal to CV, where Q is equal to amount of charges stored, amount of charges. The unit is in coulombs. So coulombs, I beg your pardon, I think the spelling. This is O, not U. So coulombs, you know, the symbol is capital C. Then the C is the capacitance. Capacitance. Then V is the voltage. Now you can also use this equation, that is C is equal to epsilon naught, then epsilon R, then the area, the cross-sectional area of the plate, then the distance between the plates. So the E naught, that is the dielectric property, dielectric property. So you can determine the capacitance. So the distance between them, the plate, is the D. Then the dielectric material property is your epsilon naught. Then the cross-sectional area of the plate, you can also use it. So yes, just as you can see in this image, um, we have the ER to be the relative static permeability, the relative static permeability, and E naught is the E naught is the how do we call it? Um, dielectric constant. Dielectric constant. You can also determine the capacitance through this equation. You can use the equation C is equal to IT over V, where 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 I is equal to the electric current, um, T is equal to time, and V is equal to voltage. So we have these three equations: first equation, second equation, and third equation. We'll take some example and we'll be done. So we have this question on capacitor. So we have capacitor that has air between each plate. So in this case, the dielectric material is air. Between each plate is connected across a potential difference of, so we have our potential difference for voltage to be 12.0 volts, and stores the charges stored is 48.0 microcoulombs. They're asking us to find capacitance. So we know that charges is equal to the voltage multiplying the capacitance. So if I want capacitance is equal to charges stored over voltage applied is equal to capacitance. And so the capacitance will be equal to, we have 48.0 by 10 to the power negative 6 coulombs over 12.0 volts. And this is going to give us, we have 48 divided by 12, and that is 4. So we are going to get 4.0 by 10 to the power negative 6 farad, or you're going to get 4 microfarad. And so this is the capacitance, the capacitor. All right, so I think we'll end here. We'll move on to the next electrical component, which is inductor.